Find the point on the graph of y is equal to the square root of x plus 1 that is closest to the point 3, 0. Here is a graph of the square root of x plus 1, and there is the point 3, 0. We need to minimize the distance between that point 3, 0 and the graph of the square root of x plus 1. And more specifically, we need to find a point along the graph of the square root of x plus 1 where the distance between these points is at a minimum. If you draw a line between these 2 points and constrain that top point to existing only along the curve, we need to minimize the distance between those 2 points. If you look near the top left of this window, you can see that I've created a cell that shows the distance between the 2 points. As I move this point along the curve, it shows the distance between the 2 points. I want to find the coordinates for that top point so the distance is at a minimum. It looks like that minimum distance happens somewhere in this area here. Right now the distance is at 1.99, now it's at 1.93, and then after that it starts going up again. So that minimum distance happens somewhere in the area of 2.5. Let's think about what we just learned by exploring inside of Desmos. We know that we have the graph of the square root of x plus 1, and we know where the point 3, 0 is in relation to that graph. We need to minimize the distance between the point 3, 0 and the graph of the square root of x plus 1. In order to do this, we need to create a point along the graph and minimize that distance. I'm going to call this point x2, y2. Now that we have 2 points, we can use the distance formula to calculate the distance between these 2 points. And since this distance is what we're trying to minimize, that means that the distance formula is our objective function. The Euclidean distance between 2 points is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Can you think of what the constraint would be for this function? We know that one of the points has to be 3, 0, so you could think of that as a constraint. But more specifically, the constraint in this case is that y has to be equal to the square root of x plus 1. This is what's constraining the relationship between the x and the y variables along the curve. So let's write out our distance formula. We can substitute in our point of 3, 0 as the x1, y1. Currently, this equation is a function of 2 variables. We need to look at the constraint function and try to replace one of the variables. And we can do that by replacing the y as the square root of x plus 1. We can simplify this by squaring that inner radical and then folding out the parentheses on the left. Then we can combine like terms and end up with the square root of x squared minus 5x plus 10. This simplified radical is what we're trying to minimize. Next, we need to find the derivative. We need to use chain rule. First, we're going to drop the exponent of 1/2 out front. And then we can subtract 1 from that exponent, so it's going to be a negative 1/2. What was inside of the parentheses is going to stay inside. And then we multiply that with the derivative of what's inside the parentheses. This simplifies to 2x minus 5 divided by 2 times the square root of x squared minus 5x plus 10. I'm going to use the first derivative test on this one. First, we need to take d prime and set it equal to 0. Then we need to consider if d prime fails. D prime equals 0 means that 2x minus 5 is equal to 0. I'm just dealing with the numerator in this case. That tells me that 2x is equal to 5, and therefore x is equal to 5 over 2. This answer is in the ballpark of what we expected it to be. We thought that the minimum distance happened somewhere around x is equal to 2.5, and right now we have x is equal to 2.5 as a possible answer. Next, we need to consider if d prime fails. In this case, it might fail because we have an x in the denominator. Set that entire denominator equal to 0. And now we need to solve for x. We could divide both sides by 2 and then square both sides. That would leave us with x squared minus 5x plus 10 is equal to 0. This quadratic does not factor, so in order to move forward with the problem, I'm going to use the quadratic formula. That would give me this. What we have inside the square root, this would end up being a negative number, 25 minus 40. Since we can't take the square root of a negative number, that means that we would find no solution when considering if d prime fails. Even though we have x's in the denominator, there is no value of x that would make the denominator 0. Next, in the first derivative test, we need to do a sign test. That means we're going to plot all of our critical numbers on a number line. We only found one critical number at 5 over 2. we need to pick values around 5 over 2. In this case, I'm going to use 2 and 3. Let's plug 2 into the d prime formula. That would give us 2 times 2 minus 5 divided by 2 times the square root of 2 squared minus 5 times 2 plus 10. And this would end up simplifying as negative 1 over 4. Now we can find d prime of 3 by substituting 3 into the d prime formula, and that would simplify to being 1 over 4. Since d prime of 2 was negative 1/4, let's put a negative sign above the 2 on the number line. And d prime of 3 was equal to a positive 1/4, so put a plus sign above the 3 on the number line. Negative d prime means that the graph is decreasing at 2. A positive d prime means that the graph is increasing at 3. Therefore, we would have a minimum point at x is equal to 5 over 2. So x equals 5 over 2 is one of our answers, but the problem is asking us to find the point on the graph that is closest to the point of 3, 0. Right now, we only know the x-coordinate of a point. In order to find the y-coordinate, we could use our constraint that y is equal to the square root of x plus 1. Let's plug 5 over 2 into that to find out what the corresponding y value would be. This would simplify to the square root of 7 over 2. Therefore, we have found that the distance is a minimum at the point 5 over 2, comma, square root of 7 over 2.